Hi everyone, welcome to Brain Blitz Audios. Today we'll be looking at the second chapter, Solutions, which is found in the syllabus of chemistry for grade 12 Cbse. Now to make this chapter easier, we're going to be using the help of a mind map. Now these mind maps are really effective tools for revision and last minute reference. As you can see, this mind map is extensive and therefore we'll be trying to explain it in stages. Stage 1 covers solutions and the types of solutions: gaseous, liquid, and solid. Stage 2 will enlist the different methods to express concentration of the solution. Stage 3 goes for solubility of solids in liquids and gas in liquids. The fourth stage deals with Raos Law and ideal and non-ideal solutions. The fifth stage encompasses colligative properties, and the sixth stage deals with abnormal molecular mass. Let's begin, shall we? Now, what is a solution? A solution is a mixture of two or more components. Now, these components can be in solid state, liquid state, or gaseous state. Now, these components can be divided into two. The component which has the maximum number of parts in the solution is termed as the solvent, and the other components are termed as solutes. Depending on the state of the solvent, we have three types of solutions: gaseous solutions, liquid solutions, and solid solutions. Gaseous solutions are further divided into three based on the state of the solute. A gas dissolving in a gas solution has the example of mixture of oxygen and nitrogen. For a liquid mixed into a gas solution, the best example is chloroform with nitrogen. And the third type is solid mixed in gas solution, and the example here is camphor in nitrogen. Now, these are the subtypes of solutions found in gaseous solutions. Moving on to liquid solutions. A gas dissolved in a liquid has the example of oxygen dissolved in water or carbonated drinks. If a liquid is dissolved in liquid, it is a liquid-liquid type of liquid solution, and the example is ethanol dissolved in water. The example of a solid mixed into a liquid is glucose dissolved in water. There are many other examples of a solid dissolved in liquid type of solution because this is very common in chemistry labs. Oxygen in palladium is an example of a gas dissolved into a solid. The amalgams of mercury with sodium is an example of a liquid enclosed in a solid. And a solid mixed with a solid would refer to alloys such as copper dissolved in gold. These are the alloys are the examples of solid dissolved in solid type of solutions. So that completes the first stage of our mind map, types of solutions. Let's move on to the second stage. Now, in order to better understand solutions, we need a quantitative analysis. And it is found using the concentration of the solution. To find the concentration, there are many ways which we can use. The first way given here is the mass by volume percentage method. Here we calculate the mass of the solute divided by the volume of the solution and multiplied with 100. Volume percentage is the second way. Here we divide the volume of the component by the total volume of the solution and then multiplied with 100. The third is mass percentage. Here we divide the mass of component in the solution divided by the total mass of solution and multiply it with 100. Component can be solute or solvent. Next, to identify components in trace quantities, we use parts per million. Now in this formula, we divide the number of parts of one or more components divided by the total number of parts of all the components of the solution and multiply it by 1 million, or 10 raised to 6. Moving on, we have mole fraction as another way to express concentration. In it, we divide the number of moles of one component, solid or solvent, divided by the total number of moles of all the components. Normality is another method. The number of gram equivalents of the solute dissolved in 1 liter of solution is termed as normality. The formula here is number of gram equivalents of the solute divided by volume of the solution into 100. Gram equivalents can be calculated as mass of solute divided by equivalent weight. Equivalent weight is molecular mass divided by valency. Next, we move on to molality. Molality, with an L, is the number of moles of solute per kilogram of the solvent. The formula is number of moles of solute divided by mass of the solvent into 100. Into 100 would give you the percentage. Molarity, the one with a R, is the number of moles of solute in 1 liter of solution. This is calculated as the number of moles of solute divided by the volume of the solution into 100. Again, we multiply by 100 to get a percentage. And that is an overview of the different methods to express concentration of a solution. We move on to the third stage, solubility. What is solubility? The term solubility refers to the ability of a solute to dissolve into the solvent. Now, in this chapter, we'll be looking at solubility of a solid in liquid and a gas in liquid. For a solid trying to dissolve into a liquid, the effect of pressure is not significant. The reason being that solids as well as liquids do not compress under pressure. Therefore, pressure has no significant effect. If we look at the effect of temperature for the dissolution of a solid into a liquid, then there are two scenarios. If the dissolution is endothermic, which means that the solubility enthalpy is greater than 0, then the solubility increases with increasing temperature. If it's an exothermic reaction, then the solubility decreases as the solubility enthalpy is less than 0. And that is an overview of solid in liquid solutions. Moving on to gas in liquid solutions. For a gas trying to dissolve into a liquid, the solubility increases with decrease in temperature. That's why most aquatic life are better off in cold waters rather than warm water. The effect of pressure for the dissolution of a gas into a liquid. Solubility increases with increase in pressure. And this leads us to a first law, Henry's law. Henry's law states that the partial pressure of gas in a vapor phase is proportional to the mole fraction of the gas in the solution. So suppose a gas is trying to dissolve into a solution, a liquid solution. Then the partial pressure of the gas in the gaseous state is directly proportional to the mole fraction of the gas in the liquid state or inside the solution. The formula here is P, standing for partial pressure, is equal to KH into X. X stands for mole fraction and KH is Henry's constant. Now, let's move on to the next stage Raos Law. Raos Law states that for any solution, the partial vapor pressure of each volatile component is directly proportional to its mole fraction. The formula for Raos Law is P is equal to P naught into X. P stands for partial vapor pressure in the solution, and P naught stands for partial vapor pressure of the pure component, whether it be a solute or a solvent, and X stands for mole fraction of the said component. Now, based on Raos Law, we can divide solutions into two types: ideal solutions and non-ideal solutions. A solution which obeys Raos Law is termed as an ideal solution. The enthalpy of mixture and the volume of mixture will be equal to 0. There will be no change in heat or volume of the mixture. So if you have two components of specified volumes, then the ideal solution of them would be equal to the sum of the volumes. However, if a solution does not obey Raos Law, it is termed as a non-ideal solution. An example for an ideal solution is N-hexane and N-heptane solution. A mixture of chloroform and acetone is the perfect example for a non-ideal solution. However, non-ideal solutions are further divided into two types, and they're given here: positive deviation and negative deviation. So the deviation is with respect to Raos Law. So if the volume of the mixture and the enthalpy of the mixture of a solution has positive deviation from Raos Law, which means that both the values are positive, then the solution has undergone positive deviation from Raos Law. Therefore, it forms minimum boiling azeotropes. Azeotropes here are solutions which have the same concentration in their vapor phase and liquid phase. Solutions with same concentration. So you cannot do fractional distillation to an azeotrope. Now, a minimum boiling azeotrope means that the boiling point of the azeotrope will be lesser than the volume of the boiling point of the individual components. Let me recap it. Suppose component A has boiling point X and component B has boiling point Y. Then the minimum boiling azeotrope, or the solution of A and B, its boiling point would be less than X and Y. Now let's move on to negative deviation. In negative deviation from Raos Law, a solution would have its mixing enthalpy and its volume of mixing as negative. What it means that the change in volume would be negative and the change in enthalpy will also be negative. These type of solutions would form maximum boiling azeotropes, which means that the boiling point of the final solution would be greater than the boiling points of the individual components, whether it be solute or solvent. Raos Law holds true for both components staying volatile, which means that the solute and the solvent has to be volatile. Let's move on to colligative properties. Now, what are colligative properties? Now, these are properties exhibited by solutions when a solvent, which is volatile, is mixed with a non-volatile solute. So the solute here is non-volatile, while the solvent is volatile. In this chapter, we'll be studying 4 colligative properties. The first property is osmotic pressure. Now, osmotic pressure would be the pressure exerted on a solution to inhibit osmosis from lower concentration of solvent to higher concentration of solvent. Osmotic pressure is represented by pi, and the formula for osmotic pressure is CRT. C stands for molarity, the one with the R, molarity of the solution. R stands for ideal gas constant, and T stands for temperature. The second colligative property is depression in freezing point. Now, this is usually observed in cold countries where we put salt on the roads to melt the ice formed on the roads. The salt lowers the freezing point of the ice, thus turning it into water and defrosting the roads. Depression in freezing point, the formula here is to find the value for delta TF, to find the change in freezing temperature. Now that is equal to Kf into W2 into 1000 divided by M2 into W1. Kf stands for freezing constant or cryoscopic constant. W2 stands for weight of the solute. M2 stands for molar mass of the solute. W1 stands for mass of the solvent in grams, and it is converted using 1000 to kilograms. So the final formula is Kf into W2 into 1000 divided by M2 into W1. The next colligative property is elevation of boiling point. And what this means is that if you add a non-volatile solute to a volatile solvent, the boiling point of the solution is higher than the boiling point of the pure solvent. Now this is represented using the formula delta TB, which means change in temperature of boiling point. Now that is represented by the formula Kb into 1000 into W2 divided by M2 into W1. Now, Kb stands for boiling point constant or ebullioscopic constant. And 1000 is the converting factor for the mass of the solvent, which is W1, and this is given in grams again. M2 stands for molar mass of the solute, and W2 stands for given weight of the solute. Now, note that W2 divided by M2 into W1 into 1000 is equal to molality of the solution. The last colligative property is relative lowering of vapor pressure. Now the formula here is given as W2 into M1 divided by M2 into W1. W2 is weight of the solute, M2 is molar mass of the solute, W1 is mass of the solvent, and M1 is molar mass of the solvent. The final formula here is P01 minus P1 divided by P01. P01 stands for partial pressure of the solute, partial vapor pressure of the solvent when it's pure. So this is the partial vapor pressure of a pure solvent, and P1 is the partial vapor pressure of the solvent in the solution. And there we've completed colligative properties. Now let's move on to abnormal molecular mass. Now, what is abnormal molecular mass? Suppose a solution exhibits colligative properties. Some phenomena occur. In some solutions, the solute is divided into further ions, thereby reducing its molecular mass, while in others, it forms polymers such as dimers or trimers, thus increasing molecular mass. So the abnormal molecular mass is defined as the molecular mass different from the expected value, and this is due to colligative properties. And now, to find out abnormal molecular mass, we use a factor called Want Hoffe factor, represented by I. The value of the Want Hoffe factor, I, is equal to normal molar mass divided by abnormal molar mass. Normal molar mass refers to the ordinary molar mass of the compound, and the abnormal molar mass is the molar mass exhibited due to the colligative properties mentioned above. And that's all from the chapter Solutions. It was interesting, wasn't it? Now, our channel, Brain Blitz Audios, is committed to delivering free education to all. To be a part of this journey, please subscribe to our channel. Thank you for watching this video, and see you soon. Until next time, goodbye.